Hello, and welcome to more modeling with functions. Why more? Because we've already modeled with functions once. They were mostly linear functions, and we're going to see that again. But we're going to do some more of it. So let's talk about what a model is. A model is an abstraction with the following characteristics. First of all, a model is able to explain present phenomena. So what's going on right now or over the period of study. It should not contradict actual data and information already known to be true, right? So it shouldn't say in 2020 there were absolutely no humans on the earth, because we know for a fact there's over 8.5 million. A model is able to make predictions about data or results. So it uses current information to predict phenomena or create new information. And so if you really want to think about a model, think about the weatherman, right? Or weather lady or weather person in general, the weather. They use models. They look at the airflow and all this airstream and all these different things, and they make a prediction about what the temperature should be. And the temperature, right, they keep predicting. They predict when the rain's going to come, and over time, because the computers are getting better and the models are getting better, there's a lot better accuracy of what's going to happen with the weather. All right, but we can't predict more than, say, 15 days with any accuracy in a specific location. We might be able to say, next week, make sure you have your umbrella. It's going to be a rainy week. But we can't say the fourth week of 2045 we don't have that kind of knowledge ahead of time. So it can only use current information to predict a phenomenon or create new information, and it always has its limitations. All right, so a fact. To model a quantity that is changing at a constant rate, this is important, changing at a constant rate, with f of x equals mx plus b, the following formula can be used. So the constant rate of change, so if the ocean is rising by 0.01 meters annually. All right, so the 0.01 is the constant rate of change. How much, what was the initial level? It was initially at sea level, but it's raising and it's still at sea level. But you know what I mean. So the amount of rate, the constant rate of change times the variable x plus the initial amount that we started with. So the constant rate of change corresponds to the slope of the graph f, and the initial amount corresponds to the y-intercept, just like they do in the formula f of x equals mx plus b. Okay, so we want to write a formula for a linear function that models the situation. We're going to choose appropriate variables. So I'm not just going to use x and y. Those are boring. Let's use variables that make sense. Read the problem first. In 2010, about 27% of U.S. homes had broadband internet access. Okay. This percentage increased on average by 1.2 percentage points per year for the next 4 years. Okay, I just want a formula that models this. So I look at, let me see, we have percent broadband access, broadband internet, percent of broadband internet, and we also have the number of years, right? We're looking at a year, 2010. We have years, 4 years. So let's make t be the time in years since 2010, because this is a good starting point. Good starting point. And let's let p be the percent of broadband internet access. So p of t is increasing, so plus, on average, right, the constant rate of change, 1.2 percentage points, but I'm not going to change that percent into a decimal, and I'll tell you why. Multiplied by our variable, add to that, what was it to start? Added to that 27. Since I'm going to write 27 as a whole number, so I know my output is already in a percentage form. I don't want to have to convert to get my formula, and then once I find my answer, I convert again. So that's it. The percent of U.S. homes that have broadband internet access in 4 years in the 4 years since 2010 can be modeled by this equation. P of t equals 1.2t plus 27. The only reason I rewrote that is because that plus for increasing, not necessary. So I wrote it just so it looks nicer. That's it. Looks nicer. In the first month of 2016, about 0.6 trillion text messages were sent. All right. The number of text messages being sent each month. So right here, number of text messages being sent each month during 2016 grew by this number, 0.08 trillion per month. But it tells us the units. Let's let T be text messages sent in trillions. And this is changing each month. Months since the first month. Months after might be more understandable. After the first month of 2016. And I know that's first month is January, but not everybody speaks the same language, so we'll just leave it at that. Math, we all speak the same. So the number of text messages based on the month grew by 0.08 trillion per month. So we're going to multiply by the number of months. I'm used to a little t as my variable here. Multiplied by the number of months. How many did we have in the first month? 0.6 trillion. So by the 7th month, we would have 7 times 0.08, which is 0.56, added to the 0.6. We'd have over 1 trillion text messages being sent by end of July in 2016. That's insane. That's a lot. My thumb hurts for you. Okay. It's not like one person was doing it. It's not that bad. Worldwide, come on. All right. So a 300-gallon tank is initially full of water and is being drained at a rate of 10 gallons per minute. We want to write a formula for a function W that gives the number of gallons of water in the tank after t minutes. So W is the number of gallons. And I can see here, initial is 300 gallons. So if I'm writing a formula, W of t equals, I know that I initially have 300 gallons and it's being drained at a rate of 10 gallons per minute. Drained, so it's going down by 10 gallons every minute. This plus sign, let's not make that red. That should be blue because we started with a positive value of gallons of water. That's it. Don't overthink it. Drained, negative. It's going down by 10 gallons every minute. And T is the number of minutes. This gallons per minute, gallons tell you the outputs of the units of the output per minute. The one in the denominator that's per, that's the units of the input. Okay, graph W and identify any intercepts. Wow. Who's doing that? Nobody's proofing my work anymore. I'm the only one that proofs my work. I don't farm that out. That's all on me. Okay, graph the function W and identify any intercepts. Well, I'm going to use this calculator that we have right over here. I'm going to go to -10 in X variable because I'm on the calculator, plus 300. And when I graph this, I'm going to think about my window. I'm going to think about how long do I think it's going to take to get all this water down. Well, I know my time's not negative. So let's go, I don't know, 50 minutes. Let's see what happens after it. Let's go an hour. And let's go an X scale of every 10 minutes. There we go. The Y values, will I ever have negative 10 gallons of water in the tank? No, because that's not possible. And I know the maximum water in the tank is 300, but I'm going to go a little above that just so that I could see everything fairly clearly. I'm going to go by 30s for no reason whatsoever. So remember our X scale. Our X scale is by 10. So if I graph this, I am going to have just the first quadrant, and my graph will look as such, with a y-intercept of 300 and an x-intercept that I could count, 10, 20, 30. It'll take 30 minutes for this to drop out. So let's look at what these mean individually. The first intercept means we start with 300 gallons of water. And this is the point 0, 300. Now the x-intercept tells us that after 30 minutes, the tank has no water. So at 30 minutes, 0 gallons. All right, fantastic. Now, if we look at this in general, if we look at just the equation, W of t equals negative 10t plus 300, our domain is all real numbers. But because this is an actual word problem that really means something, the domain of W will be the interval from 0 to 30. Because there's no need to talk about how much water is in the tank after 30 minutes. It's empty. It doesn't go on forever. This function doesn't go on forever because within the terms of this model, we're only talking about water in 30 minutes. So after 45 minutes, I don't know, the tank's just sitting there. I don't know, why are you still there? Playing on your phone? Come on, move along, do what you need to do. So you have to keep the domain in mind based on the situation as well as the equation. Now, sometimes one equation is not sufficient to model a situation, and for these we use piecewise defined functions. And my favorite all-time definition in math is piecewise defined functions because the definition is, it's a function defined on various pieces. That's it, it's a piecewise defined function. If all the pieces are linear, we call it piecewise linear function, like this example. Let f of x be 3x if negative 1 is less than or equal to x is less than 2, less than 1, looking at 1, red 2. And it could be x plus 1 if 1 is less than or equal to x is less than or equal to 2. Now, it looks like to me that this particular function starts at negative 1. Let's determine the domain. Write your answer in interval notation. So I know the parts of it are, and we'll go blue with the top part. That is from negative 1 to 1. Include negative 1, so square brackets. Do not include positive 1, because there's no equal sign, so that's parenthesis brackets. And in red, the domain of the bottom part is 1 to 2. So what does that tell me? It tells me overall, if I combine the domains of the individual pieces to get the overall domain, I start at negative 1, I go to 1, I include it, and I move on to 2. So the full domain takes into account everything going on together, whereas the individual domains are the individual pieces. Okay, let's evaluate. F of negative 2. I ask myself, where does negative 2 fit in these intervals? And I'm going to look over here. Negative 2, oh, that's not even in the interval. That's undefined. And I see what I did here now. And I see why I need to do something really quickly. Let's go ahead and make this one doable. Wouldn't that be nice? There we go. F of negative 2 is undefined. Negative 2 is not in our domain. I can't find that. F of 0. Well, 0 is in this section between negative 1 and 1. Right? 0 is in this first domain, so it's using the first formula. And finally, if I want to find f of 2, where does 2 lie? It's not in this top domain. It's in the bottom domain. X can equal 2. So I use the bottom formula to get 2 plus 1, which is 3. All right, so we want to graph this. And I'm going to use my calculator. First thing I'm going to do is I'm going to turn it on. I'm going to zoom back to a standard window. And then I'm going to stop it. Okay, I didn't stop it, but I waited it out. Here's how we graph piecewise defined functions in these graphing calculators. 3x, we put it in parentheses. And then we have to think about this compound inequality. It says x is greater than or equal to negative 1, right? Because negative 1 is less than or equal to x. So I'm going to put x and then use the test menu. X, it's open towards the x, so I want greater than or equal to negative 1. But then I'm going to put in another set of parentheses, x test is less than 1. And so I'm going to graph this really quickly. We could find just this piece of the graph. All right, so it's just that top part, which would be in blue if I had different colors on here. And then I go to the next piece. The next piece is x plus 1. What are the conditions? 1 is less than or equal to x, so I'm going to rewrite that as x is greater than or equal to 1, as well as x is less than or equal to 2. So x less than or equal to 2. And when I graph this, now it'll graph that next piece. And if we zoom in a little bit, let's zoom decimal. Takes us to a nice window. Not a nice enough window. Sometimes you got to think it through before you do things like that. And the problem was not with the x. So let's keep those in our nice values. And I know it doesn't look like 4.6 is a nice value, but it is negative 5 to 5. Now we can see the graph better. And we see this piece 3x from negative 1 to 1, and the part x plus 1 that goes from 1 to 2. So if we wanted to reproduce that on paper, we would draw the graph. When x is negative 1, I'll have a negative 3. When x is positive 1, I'll have a positive 3. That's this part of the line. And actually, I just did something there that is not correct. Let's see if I can. Nope. When we're at x equals 1, we can't use 1. We can't use it, so I'm going to use an open circle here. Solid dot because we can include it. There we go. Because ultimately, this function has to pass the vertical line test. And that probably should have went through 0 there. 1, 1. 1, 2. We'll have a solid point because when x is 1, 1 plus 1 makes 2. Add 1. So we're over here now at 2. Or equal to. Both of these ones are or equal to. That one is not. So that has an open circle. It's the only point on this entire graph that has an open circle. So is f continuous on its domain? If we knew this is what it would look like ahead of time, without the little points and this and that and the other, could we draw this without lifting our graphing utility, our pencil? or pen or crayon, whatever. No. This is not continuous. Notice how this has a little jump. It's called a jump discontinuity, but we'll get more into that in calculus. All right, it looks like when I changed a few things, I changed more things than I wanted to. There we go. Part 2 of this lecture coming up next. Particular definition, a function you'll see, a piecewise defined function frequently used in math is the greatest integer function. It's denoted with a double bar. Sometimes it just has like little lines on the bottom, sometimes called the floor function. The greatest integer function is defined as the greatest integer less than or equal to x. Say what? Here we go. Think of a number line. Let's look at the greatest integer of 2. Well, the biggest integer less than or equal to 2 is 2 itself. And in fact, the greatest integer of 1.7. What integer is less than or equal to 1.7? Well, 1.7 is about right here, probably a little closer over here, but 1 is going to be that integer. So as long as we have positive numbers, if it's an integer input, integer output. If it's not an integer input, just ignore the decimal and you have your output. However, if I am looking at the greatest integer of -2, well, -2 is an integer, it's all good. But if I'm looking at the greatest integer of -1.7, -1.7 is about here. What integer is less than or equal to? Oh, now we have to go down a value. All right, so positive numbers, you ignore the decimal. With negative numbers, you ignore the decimal and go one lower. All right, piecewise defined function. And if you want to see a quick one, I'm going to zoom back into a standard window. Here's why. If I use trace in a zoom decimal window, it generally traces well. Zoom. Wait it out because I forgot to erase the function first. If you want to graph the greatest integer function, you could go to the math menu, over to number, down to int, it's the integer function. And when you graph that, this is what it looks like. We frequently call this a step function. Step functions are a great class of piecewise defined functions that you see all over math. All right, that's it for part 1 of more modeling with functions. We're going to talk about some direct variation next in part 2. Thanks for listening.